Hello class, this is Mr. Coy. So this is a little more in depth on solving kinematics problems as well as some practice. So first off, it's going to be talking about strategies and recommendations that you should really be doing for the first 100 or so problems. Later, once you get really good at them, you can skip a lot of these steps. But for the first 100, you should be doing them. Two, we're going to go over an example with one object. You saw some of these in the kinematics equation problems. They're relatively simple. And three, two objects such as when will they meet, what will happen, how fast they be going when they meet, things like that. Alright, so first thing in your general strategies is read the whole problem. Don't read part of the problem, don't skim the problem, read the whole problem and really try to picture it. So, in coming to a stop, a car leaves skid marks 92 meters long on the highway. Assuming a deceleration of 7 meters per second squared, estimate the speed of the car just before braking. So you want to really picture what that thinks is you have a car moving probably very, very fast to leave 92 meter skid marks. Slams on the brakes, skids down the highway for 92 meters before finally coming to a stop. So it doesn't necessarily tell you velocity here, but think about what velocity must you be going to be at stop. And remember, speed is really just another way to say velocity. And this is the car before braking. Alright, next. Actually draw a picture. So, next draw an actual picture of it. Don't just picture it, draw an actual picture. You should also label said picture. So, you have some car. Leaves skid marks, 92 meters long. When it was here, we wanted to know how fast it was going. Later, it stopped, so we know exactly how fast it's going. And through this, it had to be slowing down at 7 meters per second squared. And remember, if it's slowing down at 7 meters per second squared, decelerating, that's a negative acceleration. Alright, and while you're labeling, you should be letting yourself know a variable. So I did say that our v final is 0, our v, I forgot the initial, we don't know. We do know that this was our position, also known as our change in position, because it went 92 meters. That's how much it went. We don't know exactly where it started or ended, but we know in between there it went 92 meters. And your acceleration is equal to -7. So we have everything labeled. So from here, you want to pick out which equation. So I have the 5 equations here. So what you really want to think about is which variables we have. So we kind of already established that, but just to write it out a little clearer, we have a delta x, we have a final velocity, or we need to find a final velocity, so that must also be in the equation. We have a v0, an initial velocity. That's the one we need to find. We have the final velocity, it's 0. And we have an acceleration. So we want to find something that has all of these. So you can start by looking at this. So this has an x and an x0 together. If you subtract those, you do get your delta x. So we have that. We have a v0. We have an a. We're missing a velocity that we should have, and we have time, which we don't know. Alright, this one has velocity, v0, acceleration, and x minus x0, which is together delta x. This one, same, it has a t that we don't need, and no x. These two have very little of what we need and will absolutely not be telling us the right answer, specifically because we don't have time in this case. So, in case you weren't sure, that ding 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 makes this one the winner. Alright, now that you have your equation that you want to use, you now want to go back and solve for the correct variable. Now, what I mean by correct variable is the variable we actually want to solve for. So, you want to estimate the speed at the beginning. So remember, at the beginning, that would be your initial velocity. So we want to get this one all by itself. So first off, delta x is equal to x minus x naught, so you can really just rewrite this as 2a delta x. Alright, from here, you want to subtract. Remember, undo the addition. And it must go to both sides. And now that we have that squared, we would want to square root both sides. So the final bit would be v squared minus 2a delta x equals v naught. Once you have it all set up like this, next you're going to just plug in your numbers and solve. So you have it set up the way you like, so now you just need to throw in some numbers. So we know v naught is equal to the square root of your v final. We know since it is stopped that the v final must be 0. No velocity if it's not moving. Minus 2a. Remember, our a in this case, because it is decelerating, is negative 7 meters per second. And then our delta x in this case is 92 meters. So this is just 0. So you're going to get the square root of, which is 1,288. If you square root that, you get 35.9 meters per second. So just to do a quick recap, first, read the whole problem, picture it, then draw an actual picture and label. Good labeling is very important. 3, figure out which equation to use, which is how we got to here. Then solve for the correct one, so we get this. Then plug in your actual numbers and solve. Alright, so here's our 2-object problem. So first step, read it and picture it. 2 trains speed towards each other. One train starts 1,500 meters west of the city and moves 35 meters per second east. The other train starts 1,000 meters, I realize that looks like a 6 now, 1,000 meters east of the city and moves 30 meters to the west. Where will the 2 trains meet? So now that you've read the picture, now you want to think of drawing it. So we have, let's just call this train 1. Going in this direction, it is 1,500 meters from your city, and it is going 35 meters per second. Then you have some train 2, that is 1,000 meters from the city, and it's going 30 meters per second. And let's just say this is our city here. So first off, you need to know your cardinal directions. So remember, this is east, This is west, south, north. Never eat soggy waffles. And then, so now you have your picture. Now you need to start thinking of your equations. So first off, you should make yourself a reference point. So you need to figure out where you want to call 0, because these are on the same number line. How you set it up is up to you. Preferably, for me, I would like to call this C0, so I can say, okay, this one starts 1,000 meters away, and this one, because it's on the left side, the number line is negative 1,500 meters from your spot. Then, you need to label all your variables per item. So, if we are starting with train 1, we need to start with all the variables from train 1. So train 1, we have an initial position. We have, well, we want to know its final position, but we don't yet. We know its initial velocity. We know that it's not accelerating, it's staying at the same speed. So we know that its acceleration is equal to 0. Then we have train 2. We know its initial position is positive 1,000. We know its position x2. Well, we want to find it. We know its initial velocity of 30 meters per second. And in this case, since it's moving to the left, that would be a negative 30 meters per second. Remember, direction is very, very important in physics. We tend to say that if it's going right, it's positive. If it's going left, it's negative. So the train on the left is going to the right, so it's positive. The train on the right is going to the left, so it's negative. This train also has 0 acceleration. So it may be a little difficult to see because you're right, you don't necessarily, there's no one equation that will give you everything. However, you'll find that the first kinematics equation has most of what you need. And since acceleration is 0, we can cut that part out. So you can instead set up an equation where it has x1 is equal to, I already wrote it up there, I'm not going to write it again, because I'm running out of space. So your x equals x naught plus v naught times t. So you can set that up for each equation. So for this one, you would have x1, which we don't know, is equal to 1,500 plus 35 times t. And then our second one is x2, which we don't know yet, is equal to 1,000 plus negative, or you could have just subtracted, times t. And so now you can see, and we know that x1 equals x2, because it ends up in the same spot. So we gotta figure out, where does x1 equal x2? So a good way to do this is you can set both of these problems equal to each other, because we know that they have to end up in the same spot if they meet. So you can just put your two equations equal to each other. And here you can see that, well, we can't solve for x1 or x2 yet, but we can solve for t. So this is like your systems of equations. Two equations, two unknowns. Alright, so you're going to solve for t first. Move some things over. I forgot to put my negative in there. That's why it looked weird. So you're going to get 65t is equal to 2,500, therefore t is equal to 38.5 seconds. Then you can go ahead and plug that back into either equation. I'm just going to plug it into x1 because it's there. Gosh, running out of room. Solve that and you'll have x1 equals, you get negative 153.8 meters. So if you want to put that back in perspective to your problem. So essentially on your number line, they'd be meeting at 153.8 meters west of the city. Alright, hopefully that was helpful. So the main idea with two objects, same thing. Generally, not always, you tend to use the same equation, or you solve one first and you go back and solve the other. But you need to set up two equations, generally two unknowns, such as we did here. Again, if you have more questions about a specific problem, feel free to email me. I am relatively available. I tend to reply within a day or so. Good luck with the rest of your summer homework.